Welcome back. So we have been looking at counting. So in the last few lectures we have been looking at combinatorics, which is a branch of mathematics that involves counting. A typical question that is asked is, given a set S, what is the cardinality of the set S? Now, the main question is that how is the set given? Now, most of the time, the set is not given explicitly, meaning the elements of the set are not given explicitly. Instead, it is described in words. And hence, the set S is kind of understood, but the elements of the set S is hard to understand or hard to enumerate. And so the question of counting the number of elements in the set is a valid, important, and sometimes challenging problem. So for example, one can ask things like, how many elements in the universe satisfy a certain set of conditions? Or equivalently, how many ways can you draw an element from the universe such that the element satisfies the set of conditions? Some examples that we have been thinking about is the number one, how many n-digit numbers are there in the decimal representation where no consecutive digits are same? We will be seeing the proof of or the answers to all of this question in this video. Second one is, how many functions are there from 1 to n to 1 to k that are non-decreasing? That is, if x and y are two numbers, then if x is less than y, then f of x is less than or equal to y. The third is, how many ways can you distribute n identical toffees among k kids? And the last one is the number of 0-1 strings of length n which does not have any consecutive zeros. Now, the problem of counting, as you have possibly seen by now or understood by now, that every problem is unique and one can apply different techniques to solving a problem, and you have to apply the technique that fits the problem. In fact, counting is one of the most challenging subjects in math, and in fact some of the best works of even the great Srinivasa Ramanujan was on counting. And there are some handy tricks and tools that we teach in the set of lectures that one can use to solve them. So here is the thing that we found out for the counting for selection. So namely, if you have to select k objects from n objects, then depending on certain things, namely depending on whether repetitions are allowed, meaning whether the same object can be chosen more than once, and whether the order in which we pick these k objects matters, we have got the various answers. Couple of videos earlier, we did prove all these numbers. Another important question here is how to distribute n balls into k bins. And there are a few problems that one should ask, namely, are the bins distinguishable or are the bins labeled or are they not? Are the balls distinguishable and are the balls labeled? If the balls are distinguishable, then does the ordering of the balls in the bins matter? Can the bins be empty? And are there any other restrictions? Now, at least for the first 4 such restrictions, we looked at all the possible cases. And we have got this particular matrix, namely whether the bins are labeled or not, whether the items are distinguishable or indistinguishable, and if the items are indeed distinguishable, then does the ordering matter or does not matter? Now, we had one of them that was left unsolved, namely this one, right? Namely whether bins are labeled, when the bins are unlabeled and items are indistinguishable. How many ways can you solve? Now, this one is related to how many ways can you write the integer in the sum of positive numbers. Now, why is it so? Let's see. So, I have, say, n balls, and I want to break it up into bins, but I don't care the labeling of the bins. So in other words, I want to say that, okay, I want to put 2 of them in one bin, 1 of them in the other bin, maybe 3 of them in the third bin, maybe 2 of them in this another bin, and so on. So what matters is that I have one bin here, so maybe let me complete this one. So this is a breakup of this set of 13 balls into 5 bins. Now I don't care about the labeling. So in other words, it basically looks like I have one bin containing 1, 2 bins containing 2, 1 bin containing 3, and 1 bin containing 4. I don't care about the ordering. So in other words, what do I get? I get 1, 2, 2, 3, 4, and I know that the sum of them must be equal to, sorry, this was 12 balls actually, yeah, 12. So this is one way of splitting 12 balls into 4 bins. Now I could have done a separate one. For example, maybe I could have, what I could have done is, I could have split this one, and I could also have maybe got a hold of this one, say. So in that case, I would have got 3 balls of 2 each, 2 plus 2 plus 2, and 2 bins of 3 each, right? This is 3 and this is 3, and 1, 2, 3 are 2. And this is a bin 12. So the number of ways I am writing this 12 as sum of integers is basically the number of ways I can split this n indistinguishable balls into exactly k bins where none of the bins are empty, right? So we denote this number by Pn, and the question is that, okay, how many ways can you write the integer as sum of k positive numbers? So this is when we don't want the bins to be empty, and we denote it by P and K. And as you can realize that Pn equals to sum over Pnk, where k equals to 1 to n. So when we ask how many ways can we split n indistinguishable balls into distinguishable bins, what we mean here is, into k indistinguishable bins. So this number is actually P and K. Now this P and K is of course a very well studied problem. And in fact, Srinivasa Ramanujan worked on this problem quite a lot. And while we don't have an easy way of calculating P and K, Srinivasa Ramanujan came up with a formula that is very close to P and K. We call it asymptotically similar, and the formula is extremely complicated. I want to show you the formula, and this will help you to appreciate how hard the problem is of calculating the number of ways one can distribute n indistinguishable balls into k indistinguishable bins. So here it is. So Srinivasa Ramanujan gave an expression which was basically this term, which not only has some weird objects like exponential of pi. So this term basically means this is the number e power pi by k square root of 2, 3, n minus 120 by 24. Okay. And not only does it have this thing, it also has things like a derivative and the term ak, where what is ak? Where ak is this object, which is e power pi I, where I is the complex number, minus square root of minus 1, smk. Now what is smk? And smk is this expression. Now this shows how complicated it is. In fact, this number is not exactly correct because it's a very close to being correct expression for Pn. And a few years later, Ramanujan, Hardy and Rademacher got a formula which was the exact formula for Pn, and which was, instead of the exponential, they replaced it with, so they just made some changes to this part and keeping everything else same. So in fact, this is an expression for Pn. How did they come about with this particular formula? Now that is clearly a hard problem. Right? It's clearly a very hard way of getting it. But couple of things to note here. This shows how important, how hard this counting problem can be. And it also shows that it is of such importance that great men like Srinivasa Ramanujan and all have worked on this problem. In fact, this is one of the greatest work of Srinivasa Ramanujan, of proving that Pn is actually this number. So this brings us to the kind of the end of this whole thing, where we can now know how many ways can we distribute n items into k bins. Now with this done, let us try to solve the problems that we had in our minds. So to start with, let's see how many n-digit numbers are there in which there are no consecutive digits are same. Now how does the n-digit number work? The n-digit number is something like, I have some number a0, a1 till an minus 1, right? Where ai's are either 0, 1 till 9. And a0, okay, let me imagine that a0 is not equal to 0, because if a0 is 0, then I don't have an n-digit number, right? So A0 can have 1 to 9 any one of those possibilities. Now what can A1 have? Now A1 can have any of these 10 possibilities, but it cannot have the number that A0 has got. So if A0 is 1, then A1 can have anything like 0, 2, 3, 4, 5, 6, 7, 8, 9. If A0 is 5, then A1 can be 0, 1, 2, 3, 4, 6, 7, 8, 9. So for every possibility of A0, A1 can have 9 possibilities. And what about the next one, say A2? Same. Because we are not allowed to have two consecutive digits, so whatever this A2 is, A1 is, A2 can have anything other than A1. So again there are 9 possibilities. And by this way, all these n terms can have 9 possibilities. So the answer to this question is product of all of them, which is 9 to the power n. So the number of n-digit numbers in decimal representation where no consecutive digits are same is 9 to the power n. Okay? Now moving on to the next problem. And this is an interesting problem. How many functions are there from 1 to n to 1 to k that are non-decreasing? So let's forget the non-decreasing part. Let's first ask how many functions are there. So how many functions are there from 1 to n to 1 to k? Now, how do I calculate that? Now, any of this function can send this function can send the first item to any of these k points, right? It can also send the second item to any of the k points. It can send the third item to any of the k points. So, total number of ways you can get this function is k times k times k, like this, n times, which is k power n. So this is the number of functions that are there from 1 to n to 1 to k. Good. Now if I add the question that number of increasing function, what does increasing mean? Increasing means that if x is less than y, then f of x is strictly less than f of y. Now, how many such functions are there from 1 to n to 1 to k? Now, as you can say here, that of course, if k is less than n, then I cannot have an increasing function. Why? Because how can I have an increasing function? Because if 1 goes to 1, 2 goes to 2, 3 goes to 3, I have to keep on increasing. Then n has to go to something like n, but n is greater than k. So I don't even have enough terms there. So then the number is 0. And if the opposite is true, if k is bigger than or equal to n, then what happens? If k is bigger than or equal to n, it means that I can pick n elements from this 1 to k, and once I have picked some n elements, out of this 1 to k, there is a unique way of sending this 1 to n to this set of n elements. Why? Because the 1 has to go to the smallest element in n, 2 has to go to the second smallest element, so if I pick the set A. Okay? So I say I have picked the set A. So if A is a subset of 1 to k of size n, so size of A is n, then there is only unique way of sending the set 1 to n to the set A, because I have to send the first element, the element 1, to the smallest element in A, second one to the second smallest element in A, and so on. So the number of increasing functions is the same as the number of ways I can select n objects from k, so 1 to k. So the number is equal to k choose n. Now if I make this problem a bit more complicated by asking the main question, which is this question, how many non-decreasing functions? Now again here, so the result is of course what is written there, that this can be less than, if x is less than or equal to y, then f of x is less than or equal to f of y. Now again the idea is simple. Once I pick a subset A, okay, and in this time with replacement, so size of A equals to n, but A can have multiple copies, right? Multiple copies of the same element. So once I pick the subset A with replacement from 1 to k, then I know there is a unique way of sending 1 to n to A once again. So this number here is basically number of ways of getting n objects from k objects with replacement. Okay. And how many ways can I get it? So this is equals to choosing n objects from the set 1 to k with replacement. And how many ways can I get it? Now I can quickly take you back to this old slide, and this number is basically what we are asking for, is the way in which selecting k objects. Actually I am actually asking how to select n objects from k objects, but this is just the opposite of that, with repetitions, and I don't care of the ordering, right? So it is this number. So in our case it will be this number with kn in a shift. So if I go back to where I started, this is n plus k minus 1 factorial by k minus 1 factorial times n factorial. Okay. Now let's move on to the third problem. Third problem is easy. How many ways can you distribute n identical toffees among k kids? And this is again, I have done this calculation many times, is n plus k minus 1 factorial by k minus 1 factorial times n factorial. Okay. Now let's move on to the last problem. The last problem says number of 0, 1 string of length n which does not have any consecutive 0. Now this problem is quite a challenging problem. I will let you guys to think about this problem. We will come back to the next class with this problem, and this will start us or help us to start a completely new way of calculating.